So I call this resilient HVAC hydronic systems. And when we talk about something being resilient, I had the opportunity about 30 years ago to work on a laboratory facility that specifically was involved with genetic manipulation of corn. So when I say what is resilient HVAC hydronic system, I'm talking about corn. Why do we start with corn? Well, it turns out that people have been manipulating genetic combinations in corn through sort of mixing different strains of corn and getting different results. And in recent years, like in the last, like say 30 or 40 years or so, we have been engineering corn. And so what makes corn resilient? Someone in the back who just walked in said, I thought this was about HVAC. No, it's corny. So it's drought resistant. You can manipulate the genetic characteristics of the corn to make it drought resistant. In other words, you can engineer it. It also can be engineered to be insect resistant. It's an animal food source, a human food source. It makes efficient use of fertilizer. It can generate sustainable renewable energy such as ethanol. What has that got to do with HVAC systems? Well, if you understand the basic concept of something being resilient to these different characteristics, then it can adjust to different things. So when we talk about HVAC systems, specifically hydronic systems, what is a resilient HVAC hydronic system? Well, it starts with hydronics or water. It's easier to remember the word water than it is hydronics. By the way, if you hear me say the word water, I'm from New England, and normally I say water. So I have to pronounce my T's, or else you won't have any idea what I'm talking about. So we're interested in what makes hydronics or water resilient. It turns out it's similar to corn, and it's drought resistant. It's food resistant. It's animal food source. It's human food source. Efficient thermal storage, sustainable, and energy transport. But for today's discussion, it's a little bit more than that. It's also performs well, recovers quickly, highly efficient, responds to weather extremes, responds to code changes, responds to building modifications, component and control changes, environmentally safe, interacts with renewable energy sources, and flexible design configurations. Hydronic systems have all of these characteristics, and these are the fundamental building blocks of resiliency. So I'm going to go through each one of these categories with some examples so you can get an idea of what we're talking about. So let's talk about performance. Turns out we can heat water. We use a boiler. That's one option. That burns fossil fuel, but that's not our only source for heating water. We can also cool water. That happens to be a water-cooled chiller. So we can make water cold. So we can make it hot, and we can make it cold. We can also evaporate water. And many central chiller plants use cooling towers to reject heat. But a couple of the other fun things we can do with water is that we can transfer heat from one type of medium to another. We can do it from a water-to-water heat exchanger, a steam-to-water heat exchanger, or some other more exotic fluid to water. We can do it with a shell and tube heat exchanger. We can do it with a plate and frame heat exchanger. So all of those things are considered to be performance characteristics of water. Recovers quickly, which means that we can store it at one temperature and use that at a future date and to have it recover systems quickly. We can move water. We can obviously pump it around. We can clean water. and it responds to weather extremes. So when I showed this slide some time ago, someone said, I don't really get it. Well, hydronic systems can be designed so that they do not interfere or do not interface with weather directly. You can have the overwhelming majority of mechanical equipment inside a building. If you have the need for a boiler, for example, what goes in and out of the building, usually a couple of connections, one for fresh air and one for exhaust. Those are relatively small. I'm going to show you some other options, by the way, in a minute. So in terms of mechanical hydronic systems, they can be protected from weather extremes. In this case, I have extremely cold weather, and this one is a dust cloud for extremely hot weather. So your hydronic HVAC system can be isolated from the weather quite easily. If you combine that with some other technologies, which I'll show you in a minute, you can, well, if you had a boiler, for example, you would need fresh air for combustion, and then you need to have a path for the can I say this in English? Flue gases. Sorry about that. If you were doing heat rejection, perhaps you would reject that heat to a cooling tower. So you have very limited amount of equipment that's outside, but you can also have hydronic systems that don't use any outside or weather-exposed equipment. I'll show you what that looks like in a minute. One of the other things that hydronic systems do is they respond to code changes. And specifically, I put this up here just to give you a snapshot of some of the refrigerants that are either currently being phased out or perhaps would be phased out in the future. So since hydronic systems tend to centralize the refrigeration, so if you had a chiller plant, for example, all the refrigerant would be enclosed within the chiller itself. It doesn't get distributed throughout the building. And so if you had a code change that required a difference in refrigerant type, perhaps the equipment that you currently have could use a newer refrigerant, or perhaps you would simply change out that piece of equipment that operates on a more environmentally friendly refrigerant. So it is not distributed, it's central. And someone asked me, say, well, what about a water source heat pump? That's kind of a hydronic system, and I will show you one of those. Doesn't that have a distributed refrigeration? Well, it has refrigeration at each terminal unit, but that refrigeration isn't tied to all the terminal units. So if you had a leak in one unit, all the refrigerant in the entire system doesn't leak out. It's unique to that one particular unit. Okay? So it responds very well to code changes. As the law changes, hydronic systems are resilient to code changes. And this is what I was talking about, the refrigerant being isolated or consolidated into one location. If this machine became obsolete, you could change out the machine. You wouldn't have to change out the balance of the system. So it responds to code changes quite easily. And as I said earlier, it's central refrigeration, non-distributed refrigerants. And if we're talking, once again, about water source heat pumps that have individual units with refrigerant in it, it doesn't cross zone boundaries, if you will. Okay. This is a project that I worked on about 40 years ago. And the reason I put it up here is because I like this title of, I think this is going to, yeah, Response to Building Modifications. This is actually in downtown Providence. It's a new high-rise tower, but that's not the building modification part that I wanted to point out. This little building on the left was originally called the Phoenix Bank Building. And it was part of the renovation. This building here was going to be 100% renovated as part of the tower that was going to be constructed. And although you may not see it quite clearly, but there is actually a path, a walkway, glassed walkway that connects the two buildings. So the HVAC system for the old Phoenix Bank Building was demoed and taken out of the building, and we fed chilled water from the new tower over to the existing building. And so we made upgraded, if you will, or modified the older historic building to run on a new hydronic system. So it has that flexibility. If you have an opportunity to have a new building adjacent to a historical building, you can use this technique. In terms of response to components and controls, terminal devices for hydronic systems are made up of a variety of different configurations. This first one here that I'm showing is a fan coil. So we can deliver either hot water or chilled water for that fan coil to do either heating or cooling. We can also have for a terminal unit fin tube radiation. I like that word, fin tube. Yeah, fin tube radiation is extremely popular where I come from in terms of New England, both in terms of residential and commercial applications. Panel radiators are, similar to fin tube. There are multiple companies that manufacture these now, and we actually have these in our headquarters building in Cranston, Rhode Island. And again, they're used to offset the cold glass, or the cold that comes cascading from glass. And they're very, very efficient. I always like to point out that fin tube radiation and panel radiators don't have any moving parts. There are no fans, there are no dampers. They're a very simple device, and they're extremely efficient for moving energy in and out. So you put hot water inside that and circulate it. It does a great job of heating things. Radiant floor for heating and cooling. Radiant floor for heating is very popular, but a lot of people have not had an opportunity to see radiant cooling systems in the floor. They work well in environments that are extremely dry. I think Walmart uses radiant cooling in their floors for some of their facilities that are in places like Phoenix, Arizona. As long as you circulate the water above the dew point temperature inside your radiant system, you can have a radiant cooled building. So some people are doing that. You can see the flexibility that I'm starting to show you regarding hydronic systems. These are radiant ceiling panels, and they've been used for a very long period of time for heating. We circulate hot water through these radiant panels that mount in the ceiling of a building. We typically use them on a perimeter of a building, and so we can easily heat the building. And the other application for the exact same component is radiant chilled ceilings. If we circulate chilled water above the dew point temperature, we can remove sensible heat at the perimeter of the building and use radiant devices. So if a building has existing radiant heating panels, they can also be utilized to provide radiant cooling as long as your control system is sophisticated enough and your fluid delivery system is sophisticated enough to make sure that the water temperature is always above the dew point temperature. Active and passive chill beams. Active and passive chill beams have become very popular in North America. That's the United States and Canada. And they're gaining in popularity. They're extremely popular in Europe. Almost, I can't say for sure, but almost all new construction for commercial buildings in Europe are using active chill beams. How many folks have not been involved with active chill beams? Just to get a quick survey. Oh, you haven't? Oh, maybe we should do another seminar on active chill beams. Active chill beams, the major advantage to active chill beams is that they're substantially less energy consumers than conventional systems like VAV systems. They use about 1/5 as much air that an all-air variable air volume system uses. And so you get rid of the sensible heat in a space by circulating water through the tubes. Let's see if I can point to it here. Through the tubes above the dew point temperature. A passive chill, and an active chill beam uses air to induce room air across the coil that's inside here. And a passive chill beam is just basically a cooling coil inside a box, and if we circulate chilled water above the dew point temperature, it'll remove sensible heat. So they're a huge energy saver. So this is another technology that Hydronics does extremely well. Hydronic systems are also connected to air handling units. And I've been around long enough to know that air handling units come in an unlimited combination of pieces and parts and shapes and sizes. I mean, if you can imagine it, you can build an air handling unit to do it. And most of the larger air handling units operate on either chilled water or hot water or a combination of the two. Not exclusively, but a significant number of the larger air handling units, especially the built-up and the custom-built units, use chilled water and hot water, which is a hydronic component. Okay, computer room air conditioning. There are a variety of computer room air conditioning units floating around out there. This particular one happens to be a chilled water unit. And so they can be used to, hydronics again is very, very popular for large data centers. We got involved with a project about, I think it was about 4 or 5 months ago. We don't have the project yet. We're very excited that maybe we will get it. But their central chiller plant has 52,000 tons of cooling. It's one of the larger ones I've worked on. I thought the last one I worked on at 35,000 tons was big, but this one is even bigger. So that's also hydronic. And air-to-water heat pumps are the most popular thing this week. And if you've walked around the show at all, there are multiple manufacturers that are offering air-to-water heat pumps. And again, that is a hydronic component or hydronic system. Controls. You can use anybody's controls for a hydronic system. You're not tied into one manufacturer. You can specify any control manufacturer that you want to work with your hydronic system. And you can change that control system perhaps 5 years down the road or 10 years down the road if there's something that's newer, better, faster, has more options. You're not tied into one control system. You can always upgrade your controls within a hydronic system. And that's just a smaller controller. It's environmentally safe. Since hydronic, as I said earlier, is really all about water, now you can put things in water that will make it not so environmentally friendly, but we don't recommend that you do that. Water by itself is non-polluting. It's environmentally safe. You can, under the correct circumstances, please don't misunderstand what I'm saying, under the correct circumstances, you can easily put it down a drain, you can evaporate it, you can transport it. If it leaks on the floor, it's not hazardous material. It has all of these great characteristics. So they are environmentally safe, both for our water supply and our air. See if this next one works. It also does not contribute to depletion of the ozone layer. This one over here is a little demonstration of the ozone layer. And this guy over here is about the CO2. So this is greenhouse gases, and then this is the ozone layer. As the ozone layer diminishes over time, you get more of these dangerous types of UVA and UVB ultimately finding its way to the surface of the earth. Okay, let's talk about interacting with renewable energy sources. Solar hot water panels. You can generate solar hot water. We have, actually at our factory in Cranston, Rhode Island, we have, as a demonstration unit, I think we have 10 solar hot water panels, and we make all of our domestic hot water for all of the lavatories in the building. It was this type of system. The slide on the right are photovoltaics. You can generate electricity, and you can use the hot water to supplement your either space heating or domestic hot water needs, and you can use PV panels to generate electricity to run things like fans and pumps and things like that. You can also use wind power to generate electricity to run fans and pumps. You can use ground source for rejecting heat and absorbing heat. And I like this little slide It's a little bit sort of out of order, but I talked about mechanical rooms being completely isolated from the weather. So this type of system, a ground source heat pump, I'm sorry, just a ground source, let's use that word. A ground source means that there's absolutely nothing outside the building in terms of mechanical equipment. There's no flue, there's no cooling tower. Everything is contained either underground or in the building, so it's not influenced by weather. And because of that, hydronic systems can last a very long time if they're not exposed to outside weather. Well-maintained systems, it's not unusual for them to last 15, 20, 25 years easily, these types of systems. There's a project that I worked on, it's a fairly small one, in western Massachusetts, and they have they call them residence hall now. When I was younger, they called them barracks. Oh, I'm sorry. No, I was in the service, so we called them barracks. But they called them dormitories, but now they call them residence halls, which is a nice fancy name for dormitory, right? Okay, and they have, for their residence hall, they have a ground source water-to-water heat pumps, and with their water-to-water heat pumps, they generate chilled water in the summer and hot water in the winter. And everything is 100% contained inside the building. And they actually have several older buildings that have the same system. When you go visit them, I was amazed at how clean the older systems were, because they're not exposed to the weather. They don't get any dust or dirt. They look like they're brand new. Okay, what other things do we have here? Interacts with, oh, this is another geothermal. One of the things that are buzzwords these days, ground source implies that we have some type of piping system where we have the pipe that runs underground, take advantage of the fact that the ground has a relatively constant temperature. And I can't speak for the entire country, but I know in New England our groundwater temperature is pretty constant at around 50 degrees Fahrenheit. But a geothermal system is where you actually go down low enough through the Earth's crust, if you will, and you tap into the hot, I don't know if it's called magna, I don't know exactly what the terminology is. I'm a hydronics guy, I'm not a geothermal guy. But anyway, there are places in the world where they can extract heat directly from the ground and use that to heat buildings and also generate electricity. So it's a very efficient way of doing things. All of these things are capable with hydronic systems. You can generate electricity using water. I don't know if anybody has seen any of these. There are I didn't realize, I did some research. These are reservoirs where during the off-peak period, they actually pump water from a lower river or pond or lake to a reservoir at a higher elevation during the off-peak time, and then they run the water through hydroelectric turbines during the on-peak time to make use of that. And it's a great, I was amazed at how many of these are around the world. It's not like one or two. There's like 30 or 40 of them scattered through all over the planet. And they're quite interesting. Another thing we talk about is thermal storage. Hydronic systems are quite good at providing thermal storage. So that's another way you can use a hydronic system. You can also do thermal ice storage. When ice storage, by the way, was super popular about 30 years ago, we used to have this phrase that said, ice is nice for twice the price. But ice has come a long way, and there are packaged ice storage units that you can get. Here's another photograph, by the way, of an ice storage unit. Ice can store frozen water. Let's try that. It stores energy at the rate of 144 BTUs per pound. So when we think of just water changing the temperature, say I have a pound of water, and I change, there goes that word again. Water? Yeah, you heard me. If I change the temperature of water from 70 degrees Fahrenheit to 71 degrees, and I have 1 pound, that's 1 BTU. If I have 1 pound of water and I convert it into ice, I can store 144, extract 144 BTUs. So I can make ice during the off-peak period, and I can melt it during the on-peak period. And there's another opportunity for hydronic systems. Let's see. Okay, so let me show you a couple of different design configurations. These diagrams might be difficult to see from where you're sitting, so I'll just point out the highlights so you can get an idea of what these guys are all about. So this first one here is very popular for hydronic systems, a water source heat pump. And each one of these guys has a water supply. In this case, water is circulated through these primary pumps over here through the water source heat pump. So this could be, for example, a very simple 2-story building that has 5 zones per floor. And then we can inject heat through a boiler system, maybe that's burning natural gas. And we can generate heat from a boiler system, use burning natural gas, and inject that into the loop. And if we need to reduce the temperature in the cooling mode, because these guys are going to reject heat to the loop, we can use cooling towers to extract or reject heat from the loop itself. So that's one design configuration, and they're very, very popular, by the way, these days. A twist to that is that if you don't want to burn fossil fuel, you can use a ground source, like we talked about earlier. In this case, the water source heat pump is not using any fossil fuel in terms of generating heat. It's using the ground at a constant temperature, 50 degrees. So it's extracting heat from the ground and putting it into the heat pump, or rejecting heat back into the ground. So when you design a ground source heat pump system, you have to have equilibrium between the summer and the winter. The amount of heat that you extract has to be roughly equal to the amount of heat that you reject. If you don't, then over time, your geothermal field will ice up. If you're extracting heat from the ground gets cooler over time. If that is larger than your heat rejection, then on an annual basis, the ground gets colder and colder. And in extreme cases where they haven't been sized properly, they turn into a giant ice block. You don't want to do that. But that shows you the flexibility of design configurations. So this particular one does not use any fossil fuel whatsoever. Another opportunity is to supplement your heat generating equipment. If you're forced to use, because you don't have let's say you're in an urban environment, you don't have a lot of real estate, you can't put in a ground source for heat rejection and heat absorption. You can supplement your gas-fired or fossil fuel equipment with hot water solar panels. That's like I showed you earlier. So you can reduce the amount of fossil fuel significantly by simply adding this. So one of the nice features about hydronic systems is that you can add these different things to existing systems and make them more flexible, more environmentally friendly in the future. Another configuration is a chilled water system. This is a central chilled water system using affectionately known as a economizer. That's when we, in the winter time, let's do the summertime first. In the summertime, we run typical chillers, and they generate chilled water for the distribution to a building, let's say. And ultimately, they reject their heat to the cooling tower. Well, in the winter time, we can shut off these chillers. If the wet bulb temperature is low enough, we can generate chilled water from the cooling tower and use plate and frame heat exchangers to distribute chilled water in the wintertime without running the power required for the chillers themselves. So it's called an economizer. Sometimes it's called free cooling, or sometimes they also refer to as water side economizer. They're very, very popular in the Northeast because we have relatively long winters, and we can run this type of system without any electrical use for the chillers. It saves a huge amount on not only the cost, but also your carbon footprint. This is one of the things that's becoming very popular these days is an air-to-water heat pump system. And this is a very simple residential system diagram. And you have an air-to-water heat pump that provides chilled water in the summertime and hot water in the wintertime through, I've just shown fan coil arrangement here. But you can, through the proper controls and valving, you could have hot water available in the wintertime, would feed not only fan coils, but could also feed the baseboard radiation, could feed radiant flooring systems, so they're very, very flexible in terms of that. And because it's hydronic, you can add things to it in the future. So one of the things you could consider adding is, again, solar hot water panels to supplement your air-to-water heat pump when you have, obviously, the right type of sunlight intensity and direction and stuff in the wintertime. And you can combine that. So the theme here is that hydronic systems are very flexible, and they can be combined with a variety of other systems to provide 100% of your HVAC needs. As the industry changes and new technology is added, they're very flexible and resilient, and they can adapt to that new technology. If a new control system comes out tomorrow, it can easily be adapted to that new control system. If a new refrigerant either comes out because it's required by code change or law change, it can easily adapt to that sort of thing. So in the end, turns out that not only is corn resilient, but hydronic systems are also resilient. So next time you sit down to dinner and have a corn on the cob or just niblets of corn, you can think about all those wonderful things that hydronic systems have in common with the corn that you're eating.